Okay, this is going to be further momentum chapter summary. So we're going to see new formulae here. We've got the impulse formula, which is going to be force times time is equals to the change in momentum. Then we've got the kinetic energy of a non-relativistic particle, which is going to be the kinetic energy is equals to momentum squared divided by 2 times the mass. So we get this formula. We have the kinetic energy is equals to half mv square. Multiply both sides by m. This becomes square. We're going to get m times ek is equals to, this is going to be p square. So p square over 2. So ek is equals to p square by 2m. Okay, along with this, remember the physical significance of impulse and momentum. Both are vector. Units are Newton second, or you can also say kg meter per second. So we've got a question here. It says an object of mass m has momentum p, kinetic energy e, then you have another object with momentum 2p and kinetic energy as 4e. So e is equals to p squared by 2m, and then 4e is equals to 2p squared over 2. Let's call this capital M. This is going to be small m and this is going to be capital M right over here. Okay, so now instead of e here, I'm going to put this. So we're going to get 4p squared over 2m is equals to 4p squared. 2 to the power 2 is 4, and then p to the power 2 is just p squared. That's going to give me 2 capital M. So these two m are different. Okay. So let's see after simplification what we get. So we're going to get 4p squared by 2m is equals to 4p squared by 2m. This gets cancelled out. This 2 gets cancelled out. So we're going to get 1 over small m is equals to 1 over capital M. We're going to flip both sides. We're going to get small m is equals to capital M. So even though I said that they both were distinct, they were a bit different, and that's why I wrote this as small m and capital M, turns out they're not. Okay, turns out they're the same. So the answer is going to be B. Okay, next part. Car travels along a straight horizontal road. They've given us a drag force. It acts for 15 seconds, causing the speed of the car to decrease. And then they've said, what's the change in momentum? So change in momentum is equals to the force that's acting times the time period for which that force acts, 150 times 15. That's going to give you the answer as C. Okay, so we've got another question here. It says the ball is traveling at a speed of u towards the wall, collides with the wall at right angles. The ball bounces off the wall with a velocity v in the opposite direction. The time for the collision is t, which are the following expressions gives the average force on the wall during the collision. So we've got the wall here. So I'm going to take the wall's initial velocity direction as positive, and then bounces off with a velocity v, and that direction I'm going to take negative. So remember, the force on ball is equals to the change in momentum of the ball divided by time. So the ball changes momentum, it's going to be m, final velocity is going to be minus v, and then initial velocity is going to be minus plus u divided by t. And that's going to be m minus v minus u divided by t is equals to force on ball. Okay, that's going to be the force on ball. But they want us the average force on the wall. Okay, they don't want the average force on the ball, they want the average force on the wall. So remember, if the ball collides with the wall, it's going to exert a force on the wall, and this is going to be the force on ball. And force on ball is equals to minus force on wall. They both act in opposite direction. So we put the minus sign there to show that. This is Newton's third law here, by the way. Okay, you can see this is force on ball. Force on ball. If I put a minus sign next to it, that becomes force on the wall. So now I'm going to multiply this equation by minus 1. I'm going to get minus m minus V minus U divided by T is equals to force on wall. Okay, now this minus will multiply inside and become positive, so we'll get mv plus u divided by T is equals to force on wall. Minus minus becomes plus, minus minus again becomes plus. So I hope that thing is clear as well. So we can generally write the expression like this. And that's going to be A. So that's the answer. Remember always whenever you want to go through these questions, first of all, connect it to Newton's third law. Understand these type of equations. Force on the wall is equals to change in moment. Force on the ball is equals to the change in momentum of the ball divided by time. So understand this type of equation. We were talking about the force on ball and momentum of ball, and then understand these Newton third law pair equation. And lastly, always take the direction of the initial velocity positive. Okay, so always do that. You'll have many questions like this where the ball is moving with the initial velocity in a direction. Take that direction as positive. Okay, that's my key tips for these type of questions. Okay, so let's talk about a few things here. First, let's talk about the principle of conservation of momentum. It states that the total initial momentum is equal to the total final momentum given that no external forces act. Remember to mention total as well and this last point to get 2 marks. Now we talk about 2D momentum. Momentum must be conserved in both x and y direction. Make components of the momentum, form relevant equations, and find the values asked for. You can also form, in some questions, vector triangles and use the AS vector and dot technique to solve the question. Along with this, remember external force will cause an impulse, so there will be change in momentum. External forces are forces from objects or surfaces outside the defined system, i.e. frictional force. Now, last thing we're going to go through is inelastic collision and elastic collisions. Elastic collision, the K is not conserved. Elastic collision, K is conserved. In both of the collisions, remember, momentum and energy both are conserved. Now I want you to pause the video, read the question. I don't want to waste too much time reading the question. So we've got the mass up here they've given us. So I'm just going to write here M is equals to 19.1 kg. Okay. Now they want us to show that V is equals to 1.3 meter per second. So I'm going to do the conservation of momentum in the y direction because I can see that the sum of the initial momentum in y direction is equals to 0. Hence, the sum of the final momentum in the y direction must also be equals to 0. So hence I can say here P, let's see, what is this? Let's call it A here, and let's call this B. PA cos, or not cos, it's going to be sine 50 should be equals to PB sine 30. Alright, so both of them are opposite in direction. We'll say this is positive, this is negative, and they both are going to be the same. So we'll say PB sine 30 put a minus sign plus PA sine 50 is equals to 0. We're going to get PA sine 50 is equals to PB cos, not cos, sine 30. Alright, so end up with this. We're going to get MA VA sine 50 is equals to MB VB sine 30. Okay, the mass, I think both of them have the same mass, so mass gets cancelled out. They both have the same mass. Okay, we're gonna be needing to make this VB the subject because this is what we need to find out. So VB is equals to VA sine 50 divided by sine 30. Okay, let me plug in the values now. So that's going to be 0.87 sine 50 divided by sine 30. We're going to get 1.33 meter per second, which is approximately 1.3 meter per second. Now there's other way you can do this as well. You can say that the initial momentum, when we talk about the x direction, initial momentum is equal to final momentum, total initial, total final, both are the same thing. So we could have said MA UA, this is going to be A, this is going to be B, is equal to let's call it momentum of A. We're talking about this one here, cos 50 plus momentum of B. Okay, we're talking about the final momentum, cos 30. You could have done it like this and then kind of simplified it and all of that, and you could have gotten the correct answer. It's just a bit lengthy. The other one is much easier. Usually if I see a y direction, initial momentum is 0, I'm using the y equations. Very, very easy. Not a lot of terms. So remember that as well. You don't want to waste your time. Okay, next part, they said reduce whether the collision was elastic. So whether the Ke was conserved or not. First thing, let's find that out. So we're going to find the sum of the initial Ke, and then we're going to find the sum of the final Ke. I'm just going to plug in the values straight up. Okay, I've plugged in all the values for the kinetic energy initially and then finally as well. So initial kinetic energy is going to be 27.59 joules. The final kinetic energy is going to be 24.12 joules. So 27.6 is not equals to 24.12. So some of the kinetic energy was lost. So Ke not conserved. Hence, this is going to be not an elastic collision. Okay, so I hope that question was clear. Let's move on. Okay, so question 9, it says the diagram shows the moment P and Q of two bodies that are about to collide. They merge and move as a single body. Which of the following this diagram shows the resultant momentum? Okay, so basically it's going to be kind of like this. We have P plus Q is equals to R. So these are the components and get the resultant R. Okay, so what I'm going to do is I'm going to draw them like this. So this is going to be Q and this is going to be P when they collide. Okay, so now what we can do is we can arrange them in the correct orientation. So for that I can move the Q up like this. Now what you're going to do is you're going to draw the same thing here. P, we've got Q, and now we're going to draw the resultant. We start from here, we go all the way here. This is the direction of the resultant. Okay, so the answer is going to be C. Let me point one more thing out here. So this is the resultant momentum of P and Q. Now when P and Q, they're going to collide with each other. They're going to move together as a single body. And when they move together as a single body, they're going to move in this direction. So basically, when P and Q join together, the momentum of P and Q will be the same as the resultant momentum that we had initially. And this really connects to the principle of conservation of momentum. The total initial momentum must be equal to the total final momentum. So when we're talking about the resultant, that's the total momentum, right? So that initial resultant momentum must be equal to the final resultant momentum as well. So they both got to be the same thing. Okay, so keep that in mind as well. I'm going to talk about the impulse, which is force times the time is equals to the change in momentum. So in many questions, they will give you, let's take a situation here. Let's take egg, right? So we've got two eggs here. You're going to drop one egg on a piece of cloth and the other egg on a very solid, hard surface. With a piece of cloth, the impact time will be much more. So the force will be much more spread out and it will be reduced. And with the solid surface, it will instantly collide and in a very short amount of time, it will bounce off. So the time of contact or the impact time will be very less. So the force here will be increased. Okay, so these type of questions come up a lot. There was one question where they talked about two electric cars colliding, and these cars had rubber around them as well. So that rubber deformed and increased the time of collision, so the force was reduced. Okay, so you can read this question here. It says some sports place high stresses on the bones in the body which can result in injury. Again, then a bunch of information, and then it says, explain how bending both knees when landing helps the gymnast prevent an injury. So I'm going to write the answer down, but the main point here is that when you bend the knees, the time taken to come to rest increases, and so the rate of change of momentum decreases, and basically the force is reduced, and so you're going to have less chance of getting an injury. Okay, so this is going to be your answer. Bending knees increases the time taken to come to rest, the rate of change of momentum decreases, so the force acting on the gymnast is reduced, gymnast is less likely to be injured. So we've got the same concept here, F is equals to change in momentum over change in time. The time increases, force is going to go down. And when the time increases, the rate of change of momentum is going to decrease, and hence the force goes down. Okay, the same concept with the impulse as well. So same thing, this goes up, this goes down. Okay, so that's going to be all.
And this is because regardless of whether I do or do not bend my knees, the impulse will remain the same. However, bending my knees increases the change in time and therefore decreases the force of impact on my body. Now, there are many examples where we increase the change in time during the collision to decrease the force of impact. Seat belts, airbags, automobile crumple zones, packaging foam, bike helmets.